explored for implementing signal processing in network environments. In this type of environment, data can potentially be tagged with a high-level description of the processing to be done, and the details of the implementation can be based dynamically on the resources available on the network. Many of the concepts and design techniques discussed in this text are now incorporated into the structure of sophisticated software systems such as MATLAB, Simulink, Mathematica, and LabVIEW. In many cases where discrete time signals are acquired and stored in computers, these tools allow extremely sophisticated signal processing operations to be phoned from basic functions. In such cases, it is not generally necessary to know the details of the underlying algorithm that implements the computation of an operation like the FFT, but nevertheless it is essential to understand what is computed and how it should be interpreted. In other words, a good understanding of the concepts considered in this text is essential for intelligent use of the signal processing software tools that are now widely available. Signal processing problems are not confined, of course, to one-dimensional signals. Although there are some fundamental differences in the theories for one-dimensional and multidimensional signal processing, much of the material that we discuss in this text has a direct counterpart in multidimensional systems. The theory of multidimensional digital signal processing is presented in detail in a variety of references including Dud, Gian and Mercer Rowe, 1984, Lim, 1989, and Bracewell, 1994. Point 3 Many image processing applications require the use of two-dimensional signal processing techniques. This is the case in such areas as video coding, medical imaging, enhancement and analysis of aerial photographs, analysis of satellite weather photos, and enhancement of video transmissions from lunar and deep space probes. Applications of multidimensional digital signal processing to image processing are discussed, for example, in Makovsky, 1983, Castle, Mann, 1996, Jane, 1989, Bovic, ed. 2005, Woods, 2006, Gonzalez and Woods, 2007. And Pratt, 2007. Seismic data analysis as required in oil exploration, earthquake measurement, and nuclear test monitoring also uses multidimensional signal processing techniques. Seismic applications are discussed in, for example, Robinson and Treitel, 1980, and Robinson and Durrani, 1985. Multidimensional signal processing is only one of many advanced and specialized topics that build on the fundamentals covered in this text. Spectral analysis based on the use of the DFT and the use of signal modeling is another particularly rich and important aspect of signal processing. We discuss many facets of this topic in chapters 10 and 11, which focus on the basic concepts and techniques relating to the use of the DFT and parametric signal modeling. In chapter 11, we also discuss in some detail high-resolution spectrum analysis methods, based on representing the signal to be analyzed as the response of a discrete time linear time invariant, LTI, filter to either an impulse or to white noise. Spectral analysis is achieved by estimating the parameters, example the difference equation coefficients, of the system and then evaluating the magnitude squared of the frequency response of the model filter. Detailed discussions of spectrum analysis can be found in the texts by K, 1988, Marple, 1987, Therian, 1992, Hayes, 1996, and Stoica and Moses, 2005. Signal modeling also plays an important role in data compression and coding. And here again, the fundamentals of difference equations provide the basis for understanding many of these techniques. For example, one class of signal coding techniques, referred to as linear predictive coding, LPC, exploits the notion that if a signal is the response of a certain class of discrete time filters, the signal value at any time index is a linear function of, and thus linearly predictable from, previous values. Consequently, efficient signal representations can be obtained by estimating these prediction parameters and using them along with the prediction error to represent the signal. The signal can then be regenerated when needed from the model parameters. This class of signal, 3 authors' names and dates are used throughout the text to refer to books and papers listed in the bibliography at the end of the book. Coding techniques has been particularly effective in speech coding and is described in considerable detail in Jayant and Noel, 1984, Markle and Gray, 1976, Robiner and Schaefer, 1978, and Quaitieri, 2002, and is also discussed in some detail in Chapter 2. Another advanced topic of considerable importance is adaptive signal processing. Adaptive systems represent a particular class of time-varying and, in some sense, non-linear systems with broad application and with established and effective techniques for their design and analysis. Again, many of these techniques build from the fundamentals of discrete time signal processing covered in this text. Details of adaptive signal processing are given by Widrow and Stearns, 1985, Haken, 2002, and Sade, 2008. These represent only a few of the many advanced topics that extend from the content covered in this text. Others include advanced and specialized filter design procedures, a variety of specialized algorithms for evaluation of the Fourier transform, SPE, specialized filter structures, and various advanced multirate signal processing techniques, including wavelet transforms. C. Burris, Gopinath, and Guo, 1997, Vaidyanathan, 1993, and Vetterli and Kovacevic, 1995, for introductions to these topics. It has often been said that the purpose of a fundamental textbook should be to uncover, rather than cover, a subject. In choosing the topics and depth of coverage in this book, we have been guided by this philosophy. The preceding brief discussion and the bibliography at the end of the book make it abundantly clear that there is a rich variety of both challenging theory and compelling applications to be uncovered by those who diligently prepare themselves with a study of the fundamentals of DSP. Historic perspective. Discrete time signal processing has advanced in uneven steps over time. Looking back at the development of the field of discrete time signal processing provides a valuable perspective on fundamentals that will remain central to the field for a long time to come. Since the invention of calculus in the 17th century, scientists and engineers have developed models to represent physical phenomena in terms of functions of continuous variables and differential equations. However, numeric techniques have been used to solve these equations when analytical solutions are not possible. Indeed, Newton used finite difference methods that are special cases of some of the discrete time systems that we present in this text. Mathematicians of the 18th century, such as Euler, Bernoulli, and Lagrange, developed methods for numeric integration and interpolation of functions of a continuous variable. Interesting historic research by Heidemann, Johnson, and Burris, 1984, showed that Gauss discovered the fundamental principle of the FFT, discussed in Chapter 9, as early as 1805, even before the publication of Fourier's treatise on Harmonic series representation of functions. Until the early 1950s, signal processing as we have defined it was typically carried out with analog systems implemented with electronic circuits or even with mechanical devices. Even though digital computers were becoming available in business environments and in scientific laboratories, they were expensive and had relatively limited capabilities. About that time, the need for more sophisticated signal processing in some application areas created considerable interest in discrete time signal processing. One of the first uses of digital computers in DSP was in geophysical exploration, where relatively low-frequency seismic signals could be digitized and recorded on magnetic tape for later processing. This type of signal processing could not generally be done in real time. Minutes or even hours of computer time were often required to process only seconds of data. Even so, the flexibility of the digital computer and the potential payoffs made this alternative extremely inviting. Also in the 1950s, the use of digital computers in signal processing arose in a different way. Because of the flexibility of digital computers, it was often useful to simulate a signal processing system on a digital computer before implementing it in analog hardware. In this way, a new signal processing algorithm or system could be studied in a flexible experimental environment before committing economic and engineering resources to constructing it. Typical examples of such simulations were the vocoder simulations carried out at Massachusetts Institute of Technology, MIT, Lincoln Laboratory, and Bell Telephone Laboratories, in the implementation of an analog channel vocoder. For example, the filter characteristics affected the perceived quality of the coded speech signal in ways that were difficult to quantify objectively through computer simulations. These filter characteristics could be adjusted and the perceived quality of a speech coding system evaluated prior to construction of the analog equipment. In all of these examples of signal processing using digital computers, the computer offered tremendous advantages in flexibility. However, the processing could not be done in real time. Consequently, the prevalent attitude up to the late 1% OS was that the digital computer was being used to approximate, or simulate, an analog signal processing system. In keeping with that style, early work on digital filtering concentrated on ways in which a filter could be programmed on a digital computer so that with aid conversion of the signal, followed by digital filtering, followed by deconversion, the overall system approximated a good analog filter. The notion that digital systems might, in fact, be practical for the actual real-time implementation of signal processing in speech communication, radar processing, or any of a variety of other applications seemed, even at the most optimistic times, to be highly speculative. Speed, cost, and size were, of course, three of the important factors in favor of the use of analog components. As signals were being processed on digital computers, researchers had a natural tendency to experiment with increasingly sophisticated signal processing algorithms. Some of these algorithms grew out of the flexibility of the digital computer and had no apparent practical implementation in analog equipment. Thus, many of these algorithms were treated as interesting, but somewhat impractical, ideas. However, the development of such signal processing algorithms made the notion of all digital implementation of signal processing systems even more tempting. Active work began on the investigation of digital vocoders, digital spectrum analyzers, and other all-digital systems, with the hope that eventually, such systems would become practical. The evolution of a new point of view toward discrete time signal processing was Further accelerated by the disclosure by Cooley and Thke, 1965, of an efficient class of algorithms for computation of Fourier transforms known collectively A. The FFT was significant for several reasons. Many signal processing algorithms that had been developed on digital computers required processing time several orders of magnitude greater than real time. Often, this was because spectrum analysis was an important component of the signal processing and no efficient means were available for implementing it. The FFT reduced the computation time of the Fourier transform by orders of magnitude, permitting the implementation of increasingly sophisticated signal processing algorithms with processing times that allowed iterative experimentation with the system. Furthermore, with the realization that the FFF algorithms might, in fact, be implementable with special-purpose digital hardware, many signal processing algorithms that previously had appeared to be impractical began to appear feasible. Another important implication of the FFF was that it was an inherently discrete time concept. It was directed toward the computation of the Fourier transform of a discrete time signal or sequence and involved a set of properties and mathematics that was exact in the discrete time domain. It was not simply an approximation to a continuous time Fourier transform. This had the effect of stimulating a reformulation of many signal processing concepts and algorithms in terms of discrete time mathematics, ICS, and these techniques then formed an exact set of relationships in the discrete time domain. Following this shift away from the notion that signal processing on a digital computer was merely an approximation to analog signal processing techniques, there emerged the current view that discrete time signal processing is an important field of investigation in its own right. Another major development in the history of discrete time signal processing occurred in the field of microelectronics. The invention and subsequent proliferation of the microprocessor paved the way for low-cost implementations of discrete time signal to implement most processing systems. Although the first microprocessors were too slow, discrete time systems in real time except at very low sampling rates, by the mid-1980s. Integrated Resket technology had advanced to a level that permitted the implementation of very fast fixed-point and floating-point microcomputers with architectures specially designed for implementing discrete time signal processing algorithms. With this technology came, for the first time, the possibility of widespread application of discrete time signal processing techniques. The rapid pace of development in microelectronics also significantly impacted the development of signal processing algorithms in other ways. For example, in the early days of real-time digital signal processing devices, memory was relatively costly and one of the important metrics in developing signal processing algorithms was the efficient use of memory. Digital memory is now so inexpensive that many algorithms purposely incorporate more memory than is absolutely required so that the power requirements of the processor are reduced. Another area in which technology limitations posed a significant barrier to widespread deployment of DSP was in conversion of signals from analog to discrete time, digital, form. The first widely available ADE and DIA converters were standalone devices costing thousands of dollars. By combining digital signal processing theory with microelectronic technology, sampled ND and DIA converters costing a few dollars or less have enabled a myriad of real-time applications. In a similar way, minimizing the number of arithmetic operations, such as multiplies or floating point additions, is now less essential, since multi-core processors often have several multipliers available and it becomes increasingly important to reduce communication between cores, even if it then requires more multiplications. In a multi-core environment, for example, direct computation of the DFF, or the use of the Goertzel algorithm, is more efficient than the use of an FFF algorithm since, although many more multiplications are required, communication requirements are significantly reduced because the processing can be more efficiently distributed among multiple processors or cores. More broadly, the restructuring of algorithms and the development of new ones to exploit the opportunity for more parallel and distributed processing is becoming a significant new direction in the development of signal processing algorithms. Future promise. Microelectronics engineers continue to strive for increased circuit densities and production yields, and as a result, the complexity and sophistication of microelectronic systems continually increase. The complexity, speed, and capability of DSP chips have grown exponentially since the early 1980s and show no sign of slowing down. As wafer scale integration techniques become highly developed, very complex discrete time signal processing systems will be implemented with low cost, miniature size, and low power consumption. Furthermore, technologies such as microelectronic mechanical systems (MEMS) promise to produce many types of tiny sensors whose outputs will need to be processed using DSP techniques that operate on distributed arrays of sensor inputs. Consequently, the importance of discrete time signal processing will continue to increase, and the future development of the field promises to be even more dramatic than the course of development that we have just described. Discrete time signal processing techniques have already promoted revolutionary advances in some fields of application. A notable example is in the area of telecommunications, where discrete time signal processing techniques, microelectronic technology, and fiber optic transmission have combined to change the nature of communication systems in truly revolutionary ways. A similar impact can be expected in many other areas. Indeed, signal processing has always been, and will always be, a field that thrives on new applications. The needs of a new field of application can sometimes be filled by knowledge adapted from other applications, but frequently, new application needs stimulate new algorithms and new hardware systems to implement those algorithms. Early on, applications to seismology, radar, and communication provided the context for developing many of the core signal processing techniques that we discuss in this book. Certainly, signal processing will remain at the heart of applications in national defense, entertainment, communication, and medical care and diagnosis. Recently, we have seen applications of signal processing techniques in new areas as disparate as finance and DNA sequence analysis. Although it is difficult to predict where other new applications will arise, there is no doubt that they will be obvious to those who are prepared to recognize them. The key to being ready to solve new signal processing problems is, and has always been, a thorough grounding in the fundamental mathematics of signals and systems and in the associated design and processing algorithms. While discrete time signal processing is a dynamic, steadily growing field, its fundamentals are well formulated, and it is extremely valuable to learn them well. Our goal in this book is to uncover the fundamentals of the field by providing a coherent treatment of the theory of discrete time linear systems, filtering, sampling, discrete time Fourier analysis, and signal modeling. This text should provide the reader with the knowledge necessary for an appreciation of the wide scope of applications for discrete time signal processing and a foundation for contributing to future developments in this exciting field.